So, once again, we're back with the periodic table of elements, and the topic for this video is pretty much if some element, and we're talking about the main group elements, we're not really thinking about the transition metals because we're going to be using the octet rule, and so we can't necessarily talk about the transition metals. But if you have a main group element, can you predict what kind of ion it's going to make? Now, again, based off of that, we're thinking, okay, well, is it going to make a cation, which is a positive ion, or is it going to make an anion, a negative ion? And then you need to start thinking, okay, well, what magnitude of charge? So how much charge is, if it is a cation and it does go to +1, is it gonna be +1? Is it gonna be +2, +3, so on and so forth? How can we predict that? And so predicting ion charges is actually going to be very, very important because once we start getting into ionic bonding and really thinking about that, it's going to do you very well to really be able to predict what ions are going to form. That way you actually know how much of each ion you're going to need when you need to write formulas for ionic compounds. And so the way that I'm going to show this in this video is I'm going to take it a step further where I'm going to be using the octet rule as like the driver behind all of this. And I'm really going to be focusing mainly on talking about group 3, or sorry, not group 3, period 3. Sorry. Period 3. So row 3, whatever you want to call it, right? Third period. I'm going to be focusing on that row in particular. And to explain all of this, I'm going to be using shell method. That way you guys can kind of see why octet rule is really driving all of this, because again, it's the want to achieve some level of stability. And that's why octet rule is one of those, even though it's a very simple rule where you're thinking about, okay, well, I want to have 8 electrons in my valence shell, it's actually incredibly surprising how powerful that rule really is, because it even lets you do this, which is predict ion charges for certain elements. So we're going to take it step by step and we're going to kind of move across the table. The first one that we're really going to focus on is sodium. So number 11. That's the one that we want to look at first. Number 11, that means we're going to have 11 electrons. And so if we draw the shell model for that, again, when you draw a shell model, you really just kind of draw the nucleus, whatever it is, nucleus it being positively charged. For sodium, it's going to have 11 protons. And then when you start drawing the shell model, where you're going to be focusing on, okay, well, the first shell, but second shell, and then because we are talking about the elements in period 3, we're going to need to have three shells, which means that the outer shell, the valence shell, is the third shell. And so again, from here, you just kind of use the rules that we've talked about before. You only have 2 electrons in the first shell. In the second shell, you have 8, so that's 3, 4, 5, 6, 7, 8, 9, 10. And then again, because sodium is a group 1 element, they only have 1 valence electron, and so that 11th electron goes on the outside, and there's your singular valence electron. If we were to draw a Lewis dot for that, we would have the symbol for sodium, and then we would show just that lone valence electron on the outside. And so this is what we're kind of looking at right now. Now, remember, octet rule is driving everything. And this is where you have certain things as an option. Normally you would think, okay, well, if I'm in this outer shell, I would probably want to bring in, however many electrons I need so I can go to my octet. And that's true. That is an option. For example, if we're at 1, if we want to complete the octet in that third shell, we would need to bring in 1, 2, 3, 4, 5, 6, 7 electrons to complete the octet and having them add in like that. But see, energetically, that's not really going to work. That's going to take way too much energy. Because look, there's actually a simpler route. If we undo that, and we get rid of all those electrons little by little, and we go back to the reset. There we go. That's our last electron. That's the valence electron that we started with. Okay, we want a complete octet. We can either take in 7 electrons, or there's another option. We can lose 1. And the thing is, when we lose that 1 valence electron, we actually get rid of that outer shell. And when we get rid of that outer shell, we now go down to the lower shell, and then look at that. Your outer shell now has a full octet. And so in that way, sodium has those 2 options. You can either add in those 7 electrons, or you would pick what's probably more electrically favorable, which is you just get rid of that one valence electron. That allows you to go down to the lower shell, and the lower shell is probably filled, and what that means then is that sodium is able to get its octet, and so it's happy. It's stable, it's fulfilled, whatever you want to call it. Really, the atoms don't have emotions, but if it helps you anthropomorphize them, go ahead and do it. If it makes you feel like you're more similar to it, then that's all the better. But again, now from here, you need to think about what's happening. Well, look, you gave up an electron. So that electron goes off, and it's probably going to go off to do electron things. Who the hell knows what? It's probably going to be giving itself to someone. But see, that's an electron. That's a negative charge, which means when you get rid of a negative charge, normally when you think about the sodium itself is going to have, well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 protons. And then you're going to have that balanced out normally by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. However, when you get rid of that one electron, if you look at what's happening, well, these two are going to cancel each other out, neutralize, 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 neutralize. You're going to be left over with the positive charge because you lost a negative charge, and so you get Na+. So this is going to be a +1 cation, and pretty much because all the other elements in group 1 have the same behavior, they'll have that one valence electron, they're all going to exhibit the same behavior. You just keep it that simple. And so what you can do then is that when you have a periodic table, just to make your life a little bit easier, you can literally, and I say this quite literally, just put a +1 on top of group 1. Because you can predict that they're all essentially going to do the same behavior where they're going to lose that only valence electron that they have precisely because they're all dealing with the same idea of energetics. Now, some of them are going to lose it a lot easier than others, and that would be a topic for another video. If you already know the answer, then more power to you, but that's kind of the idea. Okay, so we've done sodium. Let's move on. If we go to magnesium, we're really not going to need to change too much. We can just keep our shell model going. We're still going to need to talk about that outer shell, except now we're talking about magnesium, so I do need to write a new what's it called? Actually, let me get rid of this faster. We do need to write a new shell model and a new Lewis dot. I don't know why that word was leaving me. We need to write a new Lewis dot, and so when you have magnesium, because magnesium is in group 2A, it's going to have 2 valence electrons, and when we actually write those valence electrons on the outer shell, we're going to have 1, and then we're going to have 2. And so when we have those 2 valence electrons, again, you need to think about everything in terms of energetics. So if we have this and you're thinking about energetics, then if we think about what's going to happen, well, we have the option of adding in 1, 2, 3, 4, 5, 6 electrons to complete the octet. You can add in 6. That's a possibility. However, again, energetically, that's probably not as favorable as the other option, which again, if we reset it and we remove each of the electrons that we added, we're still at 2. However, it's either add in 6 or easiest option, energetically speaking, is you just remove those 2 electrons in the valence shell, and then you're essentially good to go. You drop down to your lower filled shell, and everything has that stability, and so that means these electrons are going to disappear. Now, what does that mean for the charge? Well, we already saw with sodium that if you lose electrons, you tend to create a cation. You make a positive ion. And so what that means then, and just to kind of show this to you, magnesium has 12 electrons that it normally have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then that is going to be along with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. However, according to octet, because magnesium was desperately trying to seek that octet, it lost not just 1 electron, but 2 electrons. And so while these guys did neutralize each other in terms of charge, the issue is that when you look at what's left over, we have 2 positive charges left over. So the ion charge that we would give to magnesium would be 2+. And so because every other element in group 2 is going to be exhibiting the same behavior, that also tells you that when you look at group 2, if you want to predict that for group 2A, most of those ions will go to 2+. This trend, you can imagine, will continue when you go to group 3A, and 3A, if you're kind of paying attention and going along, will go 3 plus, because group 3A has 3 valence electrons, and it's going to be a lot easier to drop those 3 than it would be to try to pick up 5, because again, remember, 3 plus 5 is equal to 8, than it would be to pick up those 5 to get to 8. However, something very interesting begins to happen when you get to carbon, and when you get to any of the elements in group 4. When you get to carbon, just to skip ahead to that, you can essentially look at carbon as a midpoint of sorts. Because if you're thinking about octet as you being between 0 and 8, and those being your 2 options, it is definitely something to consider as the midpoint. Because if we write the shell model for carbon, again, or sorry, not carbon, we're looking at what? What would it be? Oh, silicon, right? Silicon, carbon, same idea, but we're looking at silicon. Okay, so for silicon, again, you have the outer shell, and then you have 4 valence electrons that you're working with. Now here's the issue. You're at that perfect midpoint, which means one option is totally to add in 4. And you add in your 4 into that third valence, that last valence shell, which is your third shell. And then when you add in those electrons, something interesting happens. But the thing is, you can add 4, but then the other option is actually, just theoretically just as viable. What if you essentially get rid of your 4 electrons, and then you get rid of your entire outer shell, and then you complete your octet in that way? That is also an option. And so this is actually that kind of point in the middle where you actually begin to kind of start realizing that things are going to go a little bit different once you go past this point. Because what that's telling you then is that in the same way that if you lose 4 electrons, you would go to +4, because again, you're losing negative charge. Equally viable is taking in 4 electrons to go to -4. And so what that means then is that when you get to group 4 is the turnaround point where you essentially can write it and predict it as +or -4. Now there is a way you can predict if it's going to be positive or negative. That is not going to be the subject of this video. It's going to be one for later. But that's kind of the idea. Group 4 you can consider to be +or -4. You can add that to your periodic table and have that as a support. Now, what happens if we skip ahead to phosphorus, right? Phosphorus. Now you need to start considering that things are going to be a little different once you get here. Now when you talk about phosphorus, again, it's in the third row, third period. So it's going to have that third shell that we're going to be working with. And then in this case, because it's in group 5A, and again, if you've been paying attention to the Lewis dots, you should understand that you can pick up the valence electrons from there. If it's in group 5A, you realize then that there is going to be 1, 2, 3, 4, 5 valence electrons that you're going to be working with. However, this is now the one point where it starts to get a lot more energetically favorable to actually take in electrons, because if you take in electrons, all you need to do is take in 3 of them. And when you take in 3 of them, you have your octet. Everything is nice and complete. You're happy. That is going to be a lot more favorable than just trying to get rid of your outer shell when you already have 5. You're already past that midpoint. You're a lot closer to 8. It's going to be a lot easier just to take in 3. And so when we look at phosphorus, right, so now we're looking at phosphorus. Again, you do the electron count just to consider what's actually happening. You have 15 protons, right? There are your 15 protons. At least I hope that's 15. I should be able to count it. I'll check with the electrons right now. But you also have 15 electrons normally. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it is 15. Except now you took in another extra 3. And these 3, 1, 2, 3, are not going to be balanced out by any protons, because all of these over here have essentially neutralized the charge. And so you're left over with 3 electrons, which means because you took in 3 electrons, each one having its own negative charge, you have an extra 3 electrons. And so that means when you think about the charge on the phosphorus, it's going to be 3-. That means then that if you go back onto your periodic table and you think about what the prediction is going to look like, when you get to group 5A, these are going to go to -3. Now you can imagine then that the pattern is going to hold, because let's say let's skip ahead to group 17. So now we're looking at chlorine. If we go to chlorine, and we essentially kind of reset everything that we have, And let me just get rid of all of this very quickly. If you go to chlorine, you should realize that chlorine is in group 17. It's one of the halogens. It's group 7A, whatever you would like to call it. It's up to you. So long as you know that the main thing that you should be concerned about is that if you talk about chlorine, is that you should realize again that it has 7 valence electrons, and it's really just one away from the octet. So it's going to be far more energetically favorable for this thing to just pick up 1 electron than it would be to lose 7, because it's already that close to 8. And so it will actually pick up that last electron, and so you would essentially just kind of repeat the process. You check how much protons you have, so you look for chlorine, and then you realize that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. You have normally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 electrons. However, in this case, because chlorine has 7 valence electrons and it was just one away from completing its octet, it's just going to go ahead and take in that 1 electron, and so you have that 1 extra electron, which means while all of this charge neutralizes, you're left over with a negative charge. And so that's why chlorine, you can imagine then, is going to go to chlorine minus. And because every other element in that group 17 or 7A or the halogens, whatever you want to call them, because all of those guys essentially have 7 valence electrons, they too are also going to go to minus 1. And so you can kind of see that in the gap between -3 and -1, you can kind of imagine that group 6, already having 6 valence electrons, is going to only really pick up 2 electrons, because 6 is only 2 away from 8, and it's a lot easier to take in electrons than it is to lose. The noble gases, again, they're noble. The reason why they're called noble is because they don't like to react with anything, really. Some of them do, most of them don't. But the idea then is that those guys already have their octet. Well, in the case of helium, helium has this duet, but we don't really talk about that too much. But the whole idea is, again, the noble gases have a completed shell, and so they're not looking to either lose or gain electrons. But essentially, this is how you want to think about it. To give you a slightly, I guess, more cohesive perspective that you can use, if you want to use this, you don't necessarily have to. It's just something that I've kind of thought of eventually. If you're just talking about the main group elements, so if you're talking about group 1, 2, 3, 4, 5, 6, 7, 8A, and really only up until 7, if you think about it this way, you can kind of think about it like a hill. So if you have your groups and you have 1, 2, 3, 4A, 5A, 6A, 7A, and then technically 8A, although that doesn't really matter too much, you can think about it kind of like a hill. At least this is how I tend to remember it. At 4A is your peak, and then from 1A to 2A, you go up the hill, and then from 4A down to 7A, let me erase that because that was already going way too curvy. Okay, from 4A to about 7A, you have the lower end of the hill, right? And so the way you can think about it is, well, 1A's like to go to +1, 2A likes to go to +2, 3A likes to go to +3. Once you get to the top of the hill, it's plus or minus 4, and then you just kind of go down. It's -3, -2, -1. I have no idea if this will actually bother to help you. If you think it will, go ahead and use it. But this is actually kind of how I think about it in my head. And then just don't forget that technically the noble gases are pretty much 0. We don't really think about them too much. But pretty much this is the principle that you would use to essentially predict ion charges if you would need to use it. Now, it's totally cool to put the ion charges on your periodic table. That way you don't ever have to really remember it. But my advice would be for you to really understand how this works logically. That way you can kind of have a very good understanding of how this works. And really, if you do understand it, there's not really much of a need to memorize it. It will just kind of come to you.